Hello everyone. In this video, we're going to look at the largest rectangle in a matrix problem. But to make it more fun, I've set up a scenario. The city has given Alice a map to build a rectangular office building. This map is an n by m grid of ones and zeros. The city tells Alice that she's only allowed to build on parts of the grid that are a 1, and they want the office building to have the largest area possible. Since Alice wants to know the area of the building before she starts designing it, she's asked you to design an algorithm which will tell her the area of the largest rectangle of ones from the map given to her by the city. So if we're given this as a map, the largest office building that could be built would be this rectangle here with an area of 6. And for this example here, the largest rectangle is on the bottom right with an area of 9. Now that we have seen the problem, let's look at how we might solve Alice's problem with a brute force algorithm. The brute force algorithm just tries out all the possible rectangles that can be constructed in the matrix. It starts in the top left corner and tries out all the rectangles which can start from the top left. For each of these rectangles, the algorithm verifies if that rectangle is all ones. If it is, then it counts as a possible candidate for the rectangle with the max area. When all those rectangles are exhausted, we move the starting corner over by 1 to the right and start over. And once all the rectangles on the first row are exhausted, we move back over to the left and start on the second row. We continue this until eventually we've exhausted all possible starting points for all possible rectangles. Here's the Python code. It's pretty straightforward, and I think the runtime is pretty awful, something like rows raised to the third power times columns raised to the third power. There are probably even better brute force solutions out there, but I don't want to spend too much time discussing the brute force solution because it really isn't the focus of this video. The focus of the video is the improved solution. This solution uses dynamic programming. The idea behind it is that in order to compute the area of a rectangle, we need to know the left boundary, the right boundary, and the height. So we're going to use 3 DP tables to efficiently find this out for all the elements. Then we're going to iterate through every element and use the DP table to compute areas. Ultimately, we'll keep a running max of these areas and return the running max at the end. For this problem, I want to try and explain things in a slightly different approach than I normally do. I'm going to show a few examples of matrices along with their corresponding DP tables and try to explain why the DP table has the answer it does. After we see how the DP tables are set up, we'll explore the code and the algorithm to see how we can code in the DP tables. Let's start with the heights DP table. I'm going to call the input matrix of ones and zeros that the city gives us M. And the heights DP table DP heights. DP heights is going to represent the answer to the question, what is the height of the largest string of consecutive 1 bits using this position and above? So for this input, this is what our DP heights end up looking like. Let me go through and explain some of the elements. Let's start with the positions in our input matrix that are 0. Our question is, what is the height of the largest string of ones starting at this element? Well, if this element is a 0, the largest consecutive string of ones is nothing because this element itself, the 0, already breaks the consecutive chain. So if the input element is 0, then the answer in DP heights is just 0 as well. Let's define this case as when the input for an ij position is 0, then the DP heights for that corresponding position is 0. Now let's move on to the situations where the input element is a 1. If the input element is a 1, then we know we can continue the sequence of 1s above this element if there is any sequence at all, and we will just add 1 to that sequence. So for this example, if we look at the left column, you can notice that starting at this element, you can only have a sequence of length 1, just the element itself. So the DP value is 1. But one below it, starting at this element and above, you can have a sequence of 2 1s, so the DP value is 2. And one below that, you can have a sequence of 3 1s. So hopefully you can see how we can define the second case, where the input is a 1. We define it as whatever the answer of the DP table is directly above it, plus 1. I understand that the first row will give us an out of bounds sort of error, but let's ignore that for now and handle it later in our code. At this point, you should be able to understand all the entries in the DP table, but let's look through a few more examples just to be sure. This element is a 3 because starting at this element and above, you can string a 3 high sequence. This element is a 2 because starting at this element and above, you can string a 2 high sequence. And this one's a 3 because you can string a 3 high sequence. I would take a moment to pause the video here and trace through the elements of the DP table to make sure that they all make sense to you. But assuming you understand the reasoning, let's move on to the second DP table, the one for the left boundaries. The left elements in the left boundaries are supposed to represent the answer to the question, what is the left boundary of the rectangle with the height from DP height, which is the DP table we just discussed a second ago. For this new M input here, from our heights discussion earlier, it should make sense that this is what the heights DP table would look like. Now this is what the left DP table would look like. Let's try and make sense of the values in this left DP table. Let's start with the elements where the input is a 1. So starting with this element here, remember our question is what is the left boundary of the rectangle with corresponding height from the heights DP table. So for this element, the DP height is 2, so using the elements above and to the left, let's visualize what the largest rectangle with height 2 can look like. Notice how the left bound of the rectangle is index 1 inclusive. So therefore, the value of our DP left table of 1 makes sense. Let's look at a couple more examples. For this element, the corresponding height is 3, and visualizing the largest rectangle above and to the left, which has height of 3, what position is this rectangle's left boundary at? Well, index 2, and that is why the value in the DP left table for this element is 2. For this next element, notice that the height in the DP height table is 4. So the rectangle of height 4 looks like this. And what's the left bound of this rectangle? It's index 2, which is reflected by our DP table. Let's look at one more, this element here. Its height in the DP height table is 1, so let's draw the 1 high rectangle. And the left bound of this rectangle is 0. So that's why we have a 0 in the corresponding DP left element. So what exactly are we storing in our left DP table? Well, we're saying using the elements above and to the left, let's draw the largest rectangle with the specified height from the heights DP table. And whatever the left bound of this rectangle is, that's what goes in our DP table. Now let's go over the case where the input isn't a 1, but a 0, meaning it can't be part of a rectangle. As we discussed earlier, the DP height for any element with a 0 input will be 0 as well. Now our question is, what is the left boundary of the rectangle when the height is 0? We can kind of think of this as no rectangle existing because there isn't a rectangle with a height of 0. So conceptually, the corresponding left boundary can be a null value. But in order for our recurrences to work in our actual code later on, we can't use a null value, otherwise we might get some kind of error. So let's just set it to an arbitrarily small value, like the farthest left bound of 0. At this point, I realize I haven't shown in the code how we're going to compute all this, but I promise I will in a moment. Right now, my hope is that you just understand the reasoning behind the values in the DP table. I would recommend you take a moment to pause the video and go through the elements in M and make sure that the corresponding value in the DP left table makes sense to you. But assuming you understand the DP left values, let's go to the final table of DP right values. The DP right values are similar to the left. It's just that instead of the left boundaries we're trying to compute, we compute the right boundaries. So our question for each value in the DP right table is, using the elements above and to the right, what is the right boundary of the largest rectangle with the height from the corresponding DP height table? So for this same example of inputs, this is what our DP right table would end up looking like. Let's inspect some values where the input is a 1. Our reasoning is going to be very similar to the left boundary cases. So for example, this value here, the corresponding height value is 2. So let's use this element and those above but to the right this time to draw the largest rectangle of height 2. What is the index of the right bound of this rectangle? It's 3 inclusive, and that is why the corresponding value in the DP right table is a 3. Let's look at a couple more examples. For this element here, the corresponding height is 3, so let's draw the largest rectangle with a height of 3. Notice that the right boundary of this rectangle is index 2, so that's why the corresponding value in the DP right table is a 2. For this element, the height is 1. So the largest rectangle of height 1 we can draw looks like this, and notice how the boundary is index 4, which is why the corresponding value in the DP right table is 4. Now let's look at the values where the input is a 0, not a 1. Like the left boundary, there really isn't a rectangle that can be drawn with a 0 element, so its right boundary should be conceptually a null value. And again, I haven't shown you the code yet, but a null value is going to give us an error if we try to use it in our code. So although conceptually this should be a null value, we want to set it to some arbitrarily large value. The reasoning for large value rather than small value is that this time it's a right boundary, not a left boundary. For me, I'm going to set it to the furthest right index possible, which in this example is 4. Now that you have seen the DP tables for the height, left, and right, let's go to the code and see how we can fill in these 3 DP tables. So first, we can start off with a row and column variable, just to make it easier on ourselves in this next step, where we initialize the DP values. Each of the DP tables is just going to be a 2D table with the same dimensions as the input. For height, we can initialize everything to 0. For left bounds, we can initialize everything to the leftmost index, which is 0. And for right, we can initialize everything to the rightmost index, which is columns minus 1. Let's fill in each of the 3 DP tables, which we talked about earlier. Let's start with the easiest, which is the height. We iterate through every column and apply the formula I explained earlier. If the ij position is a 1, then we add 1 to whatever the value of the DP table is of the element directly above. If it's not a 1, then it must be a 0, and in that case, we just set the DP value to 0. As I alluded to earlier, there is one small problem with this as is. For the first row, when we try to access dph of r-1, that will give us an index out of bounds error. This is not only a problem for our DP heights table, but it's going to be a problem for the left and right DP tables as well. In order to solve this, we can add an additional layer of padding to the top of each of the DP tables. This padding row will just contain the starting values. This now means that the elements of the DP table are shifted down by 1 relative to the input. In other words, the first row of values in the input corresponds now to the second row of values in the DP tables. The second row of inputs corresponds to the third row of the DP tables. The third row of the inputs corresponds to the fourth row of the DP tables, and so on and so forth. In terms of our code, adding this padding requires a few changes. First is that the DP tables now have to all have an extra row. Second, now our outer for loop, which we are using to fill out the DP tables, is going to go from 1 to n plus 1 exclusive, rather than 0 to n exclusive. And finally, when we are checking the corresponding values in the input matrix, we have to do r-1 to compensate for the fact that the DP table is now shifted 1 lower. Okay, now that that is out of the way, let's discuss how we fill out the left boundary. First, we're going to initialize the left boundary variable, lb, and for each row, this is going to start off at 0. I'll explain what this is in a second. We're also going to iterate through the row from left to right. And if the corresponding element is a 1, then we set the DP left to the max of the left bound and the DP left of the element currently above it. Again, I'll explain this in a second. But the other case is that if the input element is a 0, then we set the DP element to 0, which as we discussed earlier is conceptually a null value, but a 0 in our code in order for us to avoid an error. We also move the left boundary over by c+1. This line of code should make sense to you, but these two lines are probably confusing you. So let me explain them and how they're going to compute what we were discussing earlier when I showed you the DP tables. Our lb variable is supposed to represent the left bound of the current string of 1s, starting at the current element and going to the left in this row. So let's say that a particular row in our input looks like this, and we're trying to fill in this value here. Again, our lb represents the left bound of the current string of 1s going to the left. You can see how for this element in M, the string of 1s going left ends on the first element. So our LB variable in this case should be 1, representing the left boundary of index 1. So you can hopefully see how if we encounter a 0, it sort of breaks the chain of 1s, and updating the LB to C+1 correctly moves it over. So now that we know what LB is, what does this max LB DPL do, and why does it make sense? Well, the LB part represents the option of using the ones on this row to start a rectangle of height 1. So in this particular example, it would look like if we were to use this as our rectangle. But now, what about the DPL R-1 part? Well, we have to consider the case that there could be elements above this and that there are also 1s. Then we shouldn't be using the rectangle of height 1 as the left bound, the LB, but rather we should be using the left bound of whatever the rectangle involved in the upper element is. We take a max here because if there are elements above it, then potentially the left bound of the rectangle involving the elements above is farther to the right and more restrictive. So we have to take the more restrictive option, otherwise we could end up with invalid rectangles. I have to admit that this part of the algorithm is really hard for me to explain, so I'm sorry if you're still confused, but you might find it helpful to trace through a few examples on your own and try to figure out why it works. Anyway, assuming you understand this left bound, then the right bound should also make sense. We do a similar thing, except this time, we start the RB on the rightmost index, and we iterate from right to left rather than left to right. Now at this point, our code is quite messy, but we can do a few things to shorten it up. First is that we can realize that the left bound and the height iterations both go from left to right, so we can combine those together. Another thing is that these lines, which I have highlighted in green, these handle the case where an input element is 0. But notice how we initialize the DP table elements to these by default already up here at the beginning when we created the DP tables. So these lines, although they help us conceptually understand what's going on, they don't do anything in the actual code, so we can get rid of them. Okay, now that we have a bit more space to work with, at this point we have filled out the left boundaries, the right boundaries, and the heights. So now comes the easy part. We just need to go through every element and use these DP tables to compute the area. We have a max area variable, which we will ultimately return. And if an element in the input matrix is a 0, then we know we can't use it for a rectangle, so we just ignore it. But if it's a 1, then we proceed to compute the current area. The current area is the width, which is the right boundary, minus the left boundary. But since both those are inclusive boundaries, we have to add 1 to compensate. And for height, we can just pull that from the DP heights array directly. Once we have computed the area, we just take the max of it and the current max area, effectively keeping a running max of the areas we've seen so far. And finally, we return the max area, which should hold our correct answer. Last but not least, let's look at time complexity. The analysis is pretty straightforward. We have outer for loops, which iterate through the rows, and we have nested inner for loops, which iterate through the columns. For each inner iteration, we just do constant time operations. So our overall time complexity is O of rows times columns, and if we let n be rows and c be columns, then this is equivalent to O of n times m. For space, we need rows times columns space for our DP table, so our algorithm space complexity is O of n times m. But if you notice, we only ever need the row directly above in the DP table. So there's a pretty easy conversion to O of n space, which I encourage you to try and find once you understand this solution. Well, this was a really long explanation, and to be honest, I thought this problem was really hard to both solve and make a video and explain. So if you are at all confused by the explanation and have any further questions, feel free to leave a comment and I'll do my best to get back to you. I do hope this video at least helped your understanding in some way though, and if you did find it useful, please consider liking the video and subscribing to support me and the channel. But with that, thank you very much for watching, and good luck on all your interviews.